STA 3532 Statistical Quality Control Lesson 3 Control Chart for the Variables Part 2. In the previous part of the lesson we discussed how to write the control limits for the X bar charts, R chart and S chart. Now we discussed furthermore about control limit, specification limit and the natural tolerance limits. Control limits are the functions of the natural variability of the process. We know that how to find the control limits we discussed in the previous part of the lesson, and natural tolerance limits represent the natural variability of the process, usually set the 3 sigma from the mean, right? So if now we know how to find the sigma, we discussed R bar over D2, and also if S bar is given, so S bar over C4 is also a method for find the sigma. Then if you found the sigma process mean, it means X double bar plus or minus 3 sigma, that is the natural tolerance limit. And specification limits are determined by the developers and designers. So there is no mathematical relation between the specification limits and the control limits and the natural tolerance limits. They determined by the developers and the designers. And furthermore, about the specification limits, natural tolerance limits and the control limits, there is here I mentioned that there is no mathematical relationship between the control limits and the specification limits. Do not plot the specification limit on the charts. We are not plotting the specification limits on the charts. Cause in confusion between the control and capability. If individual observation are plotted, then specification limits may be plotted on the chart. So rational subgroups. X bar chart monitors the between sample variability, and R chart is monitors the within the sample variability. So these are two types, X bar and R. X bar monitors the between sample variability, and the R bar monitored the within sample variability. And change in the sample size on the X bar and R charts. So if we change the sample size, there are some differences we need to be in for the charts, that is explained in there. In some situations it may be interest to know the effect of change in the sample size in the R bar and X bar charts need information. So here to find these things we need these things: R bar old and R bar new, N old and N new, and D2 old and D2 new. If we new these values, so we can do the calculations to find the new X bar charts and the R charts. So these are the equations to find the control limits when change the sample size. So for X bar chart we can write upper control limit equals X double bar plus A2 times D2 new divided by D2 old into R bar old, and the lower specification limit of X bar is equals LCL equals X double bar subtraction A2 times D2 new over D2 old into R bar old. These things for the X bar chart. If R chart is used, again upper control limit equals D4 times D2 new over D2 old into R bar old, and control limit equals center line equals R double bar, it means R bar new equals D2 new over D2 old equals multiplied by R bar old. And also upper control limit maximum of these two. If 0 O, this value D3 times D2 new over D2 old R bar old, it means if this part is get the maximum value, then you need to what's negative value, this part is get the negative value, you need to take the maximum of this 0, means upper control limit as 0. If that is positive value, you need to take that value. If the process mean and variance are known or can be specified, then the control limits can be developed. So process mean and variance is are known. Here if it is known, the process mean and variance, you can write the X bar charts in like this way. Now if it is known, UCL upper control limits mu plus A sigma and center line mu LCL is mu subtraction A sigma. If process mean is known and if R bar chart is equal, right, UCL equals D2 times sigma and center line equals D2 times sigma, and lower control limit is equals D1 sigma. We'll do examples to understand the following things. That is the example. To illustrate the above procedure, consider X bar and R charts developed for the handbrake process in example. These charts were based on sample size of 5 wafers. Suppose that the process exhibit the good control. The process engineering personnel want to reduce the sample size to 3 wafers. Now earlier 5, now it is reduced to 3. Sample size reduced to 3. Then variable sample sizes. Set up the new control charts. Okay. So to set up the new control chart, so we need to the old values, no? It means n old we know. What is old value? Earlier we had 5. Now n new is, that is changed to the 3. Now sample size is 3. And we found X bar earlier, that's the value is, I am taking the previous example we discussed in the previous video. I think X bar values in the somewhat there. At the beginning, no, here where X bar, here 1.5056, then X bar 1.5056, and what we need, D2 new and D2 old. D2 old means for 5, then D2 new. This is sample size 3. D2 old is here D2. If a sample size is 5, that is this value. If sample size is 3, this value. Then D2 old equals 2.236. D2 new equals 1.693. You need again another value, R bar old also, no? R bar old, this one 0.3251, 0.3252, no? Right, now we can substitute those values and find the new upper control limit. UCL equals X double bar 1.5056 1.5056 plus A2. A2 is now new value, no? A2 is for 3. A2, that is 1.023. 1.023. R D2 new equals 1.693. D2 old equals 2.236 into R bar old equals 0.3252. If you simplify this, you can find upper control limit as 1.7575. Try this. I am not going to simplify this and show you. This is the answer. And LCL also you can find, substitute those value for this one again, then 1.2537. you may try this, that is not difficult one. So again, as same way here, only the difference is minus, all the other values are same. This is for the X bar chart. So we need to find the R bar chart also. This is the D2 new R old. We found that D4 is D4 need, no? D4 is this one, 2.574. D4 equals 2.574, and we need D3 here, no? D3 is 0. D3 is 0. Then we can substitute upper control limit. D form is 2 times 574 into R D2 new. D2 new equals 1.693. 1.693 divided by D2 old, 2.236. 2.236 into R bar old. R bar old means 3252. 0.3252. 0.3252. By simplifying this, you can take the value as 0.6338, and here center line equals R bar new, that is D2 new equals 1.693 over 2.236 into 0.3252 R bar old equals, the value is, you can take 0.2462. Simplify and try. Then LCL equals, since D3 is equal 0, this part is 0, then here 0, here 0, maximum is 0 and 0 equals 0, right? Since this value D3 equals 0, this part 0, then LCL equals maximum of 0 comma 0, then LCL equals 0. These are the specification limits. This, if you change the sample size according to the this way, that other control limits also changed. Right. Then the operating characteristics function we normally we called OC curve. The ability of the X bar and R charts to detect the shifts in the process quality and describe their operating characteristics curves. It means we need to find the defectives. X bar and R charts we are used to find the defectives in the process control. Consider the operating characteristics OC curve for an X bar control chart. The standard deviation sigma is assumed known and constant. So here we assumed sigma is known and constant value. It is not changed. If the mean shift of the in process value, say mu naught, to another value mu1, it means in control, then mean shifts, mean change. Standard deviation constant, then mean shift to in control value mu naught to mu1, then mu1 we can find mu naught plus k sigma. So keep this equation in mind when we are doing some calculations. We need this equation also. If we need to find the shifted mean, that mu1 equals mu naught plus k sigma. That is not explained in differently. So in here it is mean, if you need to find the shifted mean, that is the equation, mu1 equals mu naught plus k sigma. The capability is not detecting shifts on the first subsequent samples beta risk. There is a beta risk. It equals this we can lower control limit, in between lower control limit and upper control limit. Then that shifted mu0 and mu0. Then we can find the OC curve. So here we can substitute, since X bar is normally distributed, then upper control limit, then here these values. But however, if you substitute this shifted mean and those things, but look at this one also, because here sometimes we need this for our calculations. That's why I need to explain it, no? And the upper and lower control limits are LCL equals mu naught plus L sigma over root 10. Why? That shifted mean we substituted for there, and lower control is mu over L sigma over root n, right? So then new shifted mean here substituted, and if you simplify and phi denotes the standard normal cumulative distribution function. This is normal distribution function. So this is reduced to the beta equals phi times L minus k root 10. This phi is normal distribution, subtraction phi times minus L minus. You have to remember this one. This is the function of the OC curve. So if you have to solve the problem related to the OC curve, that is included in your tutorial, so you have to use this equation. And this is the example for the OC curve. Suppose that we are using an X bar chart with L equals 3, the usual 3 sigma limits. Here this is a limit that usually we are taking the 3 sigma limit, then L equals 3, and a sample size that n equals 5. Wish to determine the probability of shift mu naught equals mu1 equals mu naught plus 2 sigma. Then that's a shifted mean. It means mu1 equals mu naught plus k sigma. Here k equals 2. You need to determine the k. How that? This is a shifted mean equation. So that is a general equation is that mu naught plus k sigma. So then here k equals 2. Now if since k equals 2 in there, we can substitute the values for this equation, and we can find the beta phi. L equals 3 given, and n equals 5. We found k. Then L 3 minus 2 root 5 subtraction 5 minus 3 subtraction minus 2 root 5. So beta, if we 2 root 5 here come minus 1.47 minus 5 times here, if you simplify this, minus 7.47. then beta we can find here that normal probabilities is given here 1.47 minus 1.4. here there are 7777 here, this value it's come 0.0708. subtraction 7 is not there, that is here approximated to the 0, so that is 0. Then beta is approximately equals 0.078. so beta means that that is error, that it means probability. Beta equals probability of not detecting errors, or not detecting defectives. We can write defectives, no? Not detecting defectives, right? If we need to find the probability of the detecting at the first shift, probability of detecting at first shift, right? Not detecting is beta, then detected means 1 minus beta, then no. So for this 1 minus 0.07708, then if you substitute, then here 2992, no, then it's come 0.9292. This is the probability of detecting the defectives in the first shift, 0.9292. it means that's most probably that is detected, no, it means that is a good process. these things we can find this using these examples. I think you have to try this. Then if you doing that, if you have sometimes maybe some little bit confusing, doesn't matter, try the tutorials, then you can understand this and do these things again in yourself without looking this video. Take the only this write this example and do it in yourself, then you can understand easily. And note, then here sometimes that ask these types of question. So find the probability which detects the defectives in the third shift, that is not defect in the first shift. Then here that defect that detected the first shift, that is it's come as 1 minus beta. So if it is not detected that not detecting, that is beta, no? Then if it's come third time, it means first time is that is not detecting, that beta. Second time that is not detecting, again beta, it means beta square. In third time it is detected, it means 1 minus beta. So we can use this equation then, no? The probability that the shift will be detected on the rth subsequent sample is the simply 1 minus b times the probability of not detecting shift on the initial r minus 1 sample. So it means 2. If r equals 3, it means beta square times 1 minus beta. Then probability which detects, we can write now here r equals 2, r equals 3, it means beta square times 1 minus beta. So beta we found as 0.0708. So 0.0708 square 1 minus 0.708. So it means 0.0708 square. Earlier we found the value of this 0.9292. If you simplify this, you can take the answer as 0.0047. This is the probability of detecting at the third shift. Average run length. In general, the expected number of samples taken before the shift is detected. If the simply the average run length, we discussed this in that lesson 1 or 2. So anyhow, now we are going to simplify that equation. Then it means average run length is the before find the defectives, how many items are taken from the sample. So then it can be finds AR, that is there is another equation, average run length equals 1 over alpha means 1 minus beta. So it is easy to we are finding the beta, no? So it is easy to write this equation, 1 over 1 minus beta. Then here average run length, we can find the above equation, 1 over 1 minus beta. Beta we found as 0.0708. So again 9292, no? 1 divided by 9292, 1.076. So it's come 1.0. This is the answer. Average run length. Okay. Construction of operation of x bar and s charts. So then x bar and s chart. First, s bar is an unbiased estimate of sigma squared. S square is this unbiased estimate of sigma square. Second, s is not unbiased estimate of sigma. S is an unbiased of estimate of C4 sigma. Then where the constant of C4, the standard deviation we can write is as this way. So sometimes these equations you need to, when you have to use when we are solving the problems. So keep these things in your mind. and then if sigma is given in the control limits for the S charts. So if the sigma is given, so you can use these equations. UCL equals B6 times sigma, and CL equals C4 times sigma, LCL equals B5 times sigma. Only you can use this equation when sigma is given. Otherwise, if sigma is not given, so you have to use these equations in the S charts, S bar charts. UCL equals B4 times S bar, CL equals S bar, LCL equals B3 S bar. So here you need to find S bar, no, so using this method. But if sigma is given, no need to find S bar, you can use these equations to find the control limits. And X bar chart when using S charts. So this is a relationship between the X bar chart and S charts. The upper and lower control limits of X bar charts are given as. So if S bar is known, you can write the control limits of X bar charts. Upper control limit is equals X double bar plus A3 times S bar. Lower control that's center line equals X double bar. Lower control limit equals X double bar minus A3 times S bar. And estimating the process standard deviation of if S bar is known, so you need to find the C4 from the table. Then process standard deviation of sigma can be estimated by sigma hat equals S bar over C4. So we will do simple examples to understand the following equations. So that is the example. So only in the questions only this part is given, so I add this part also, because this part in the box, because you know then how to find the X bar and S, because I explained these things in the previous examples. So anyhow, you need to find these X bar values and S values by using the calculator, or if you like you can do the manual calculation also. But for X bar that is not a problem, but when you are finding the S value standard deviation, I think it is better to use a calculator. Otherwise it is difficult to do the calculation within the given time in your examinations. So practice to find the S bar using calculator. Then according to this value, construct the X bar and S charts. So you can find X bar equals sigma xi over m. Sigma xi here given 1850.028 divided by 25, then the answer is come as 74.001. Same way you can find the S bar also. S bar, this value divided by 25, it comes 0.0094, right? So you knew that how to take X double bar and S bar we discussed in the previous lessons. So then we can write the X bar chart. X bar chart upper control limit equals X double bar plus A3 S bar. X double bar equals 74.001 plus A3. Now sample is 5, no, 5 size, then A3, this value 1.427 times S bar 0.0094. If you simplify this, you can take 74.0145, right? Try this. And control limit CL equals center line X double bar equals 74.001, and lower control limit you can find X double bar minus A3 S bar. So again X double bar 74.001. subtraction 1.427 multiplied by 0.90094. If you substitute simplify this value 73.9877, you can take the answer. And these values for the X bar chart, so you can use this chart also. Then upper control limit equals before S bar, before n equals 5, b4 equals 2.089 into 0.0094, that is 0.0196, and center line, that is S bar, equals 0.0094, and lower control limit equals b3 S bar, then b3 equals 0 multiplied by S bar, then value is 0. These are the control limits for this one. So I think that is enough for your understanding. Anyhow, you have lecture notes. There are some more in that lecture notes, so go through those notes also, and try to understand the things included in these two videos. I think if you can understand those things, it is easy to solve the problems in the tutorial 2, and also the questions in the examination paper. I think most questions will be prepared based on lesson 3, and also the next lesson we are going to discuss lesson 4. So clearly understand this lesson and solve the problems related to these concepts, so then you can get the highest marks for your examination. And do the problems again in yourself, and try to do the tutorial 2 with the help of these lecture notes and the explanation. Hope you can do it well. So that is end of this lesson, chapter 3, control charts for the variables, and we will meet in the next lesson in the next time. So thank you very much.